All right, let's talk about statistical models. There's a ton of them, and it can feel like you're trying to navigate a huge, dense forest without a map. Well, today, we're going to draw that map together.
Seriously? Have you ever felt completely overwhelmed by all the different models out there? You see all these acronyms, GLMM, ANCOVA, and your head starts spinning? But what if I told you there's a really simple, logical way they all connect, that they're not just a random list of tools, but a family tree?
So here's our game plan. We're going to start with one single foundational model, our hero, if you will. Then we'll see what happens when we start breaking its rules and how that leads us, step by step, to all these other specialized tools. And by the end, you'll have a simple mental map to navigate it all yourself.
Okay, part 1. Our journey begins right here with what I'm calling the perfect world model. And our hero in this story, it's the general linear model. This is ground zero for basically everything else we're going to talk about.
The general linear model, or GLM, is an absolute workhorse in statistics. If you've ever run a simple linear regression or an ANCOVA, guess what? You've used a GLM. It's powerful, it's pretty straightforward, and it's designed to find a nice, clean, straight-line relationship between your variables. But, and this is a big but, its power comes with some very, very strict rules.
You see, the GLM assumes that your data is, well, perfect. It expects your outcome to follow a beautiful bell curve. It expects every single data point to be totally independent from every other data point. It assumes there are no major outliers, no measurement errors. You get the idea. It's a model built for a perfect world.
And that's the whole point, isn't it? Real-world data is messy. It almost never follows all those perfect rules. So what happens when our data breaks these assumptions? Well, that's when our map really starts to get interesting.
So let's talk about the first and maybe the most common rule that gets broken. That whole assumption about your data needing to fit a perfect bell curve.
Just think about the kind of data you actually work with. What if you're trying to predict if a customer will buy a product or not? That's a yes or a no. Or maybe you're counting the number of mistakes on a production line. That kind of data doesn't look anything like a bell curve, and our basic GLM just can't handle it.
And this brings us to the next stop on our map, the generalized linear model. Notice the name? Just one word different. Instead of being locked into that bell curve, this whole family of models can handle all sorts of different data shapes. It cleverly uses something called a link function to sort of bend the data so it can still find a linear relationship. And this is what gives us amazing tools like logistic regression for those yes-no outcomes or Poisson regression for count data.
So just by relaxing that one single rule about the bell curve, we've suddenly opened up this huge new territory on our map. Now we can actually model a much, much wider range of real-world problems. It's a massive upgrade. All right, on to the next big challenge. What do we do when our data points aren't actually independent of each other? When they're clustered? And this happens all the time, right? If you're measuring students in the same classroom, their scores are probably more similar to each other than to students in a totally different school. If you take blood pressure readings from the same person every hour, those readings are obviously related. In all these cases, that core assumption of independence is broken, and if we ignore it, our standard models can give us totally wrong answers.
So to solve this, our map splits into two main paths. If your question is about the average effect across the entire population, like, on average, does this new drug lower blood pressure? Then you'd go down the path of generalized estimating equations, or GEs. But if you're more interested in the individual variation, like how does the drug's effect differ from patient to patient, then you'd head down the path of mixed effect models. See? They're two different tools designed to answer two very different questions about the exact same kind of clustered data.
So, we've dealt with weird distributions and clustered data. But beyond that, our map has this incredible toolkit full of specialized models for all sorts of specific problems. And this is where the map just explodes with possibilities. You know, for almost any rule you can break, some clever statistician has invented a tool to deal with it. Got a few crazy outliers that are messing up your results? There are robust models for that. Are you analyzing how long it takes for something to happen, like equipment failure? That's a job for survival models. Worried that the variables you measured aren't perfectly accurate? Yep, there's a whole class of models for that too.
So the real key here is not to get intimidated by the complicated names. Honestly, every single model, no matter how scary it sounds, is really just the solution to a specific real-world data problem somebody had. Don't think of it as a list to memorize. Think of it as a library of solutions just waiting for the right problem.
So let's bring this all together. How do we actually use this map in the real world?
How do we get from our question to the right tool for the job?
Well, it's actually a pretty simple 4-step process. First, and most importantly, get crystal clear on your research question. What are you actually trying to find out? Second, really look at your data. What does it look like? Is it counts? Is it clustered? Third, compare your data to that perfect world model we started with and figure out which rules your data is breaking. And fourth, you just use those broken rules as signposts on the map to guide you to the right family of models. It's that simple.
If you only remember one thing from all this, please let it be this. Those assumptions, they aren't just a boring checklist. They are the legend for the entire map. Understanding them is what gives you the power to find your way from a simple linear regression all the way to the most advanced and specialized models out there.
So in the end, this whole way of thinking completely changes the question we should be asking. We stop asking, what's the fanciest, most powerful model I can use? And we start asking a much, much better question. What story is my data trying to tell me, and what model do I need to help tell that story accurately? If you just listen to your data, you'll always find your way on the map.